Hello everyone. We want to complete our topic pressure. It's from one topic and actually it's our third topic now, and it's still Teacher Nyangoya. Once you want to give some remarks, my mobile number is already 0724814940 and the email is nyamirai2@gmail.com. So we had finished the first 5 objectives, that is divine pressure, force acting normally per unit area, SI unit is Pascal, then determine pressure exerted in solids where pressure is force over area, and we want maximum pressure is force over minimum area, maximum pressure is force over minimum area, minimum pressure is force over maximum area. Describe experiments that investigate factors affecting pressure in liquids, and that is density, and height, and that's depth. We also derived the formula of pressure in liquids, where it's density times G times H. Then we stated the principle of transmission of pressure in fluids, and we ended up with the application of the brake system. And today we want to start on atmospheric pressure, then state and explain the applications of the atmospheric pressure, then solve numerical problems involving pressure. Now, atmospheric pressure. This is the pressure exerted on the Earth's surface by the column of air around it. This is the pressure exerted on the Earth's surface by the column of air around it. We are surrounded by air. This air, there is a lot of weight of air above us, and therefore it is like somebody who is in water. When you are deep down in water, already there is a lot of water above you, and therefore you experience pressure with respect to how deep you are. So we are on the earth, which is full of air column, and therefore we experience atmospheric pressure. Some examples on how prove that atmospheric pressure works. Take, for example, a jerry can, take a container like say the sun water container, then have hot water in the bottle. Close it tightly, then leave it for some time, or boil some cold water. After some time, you will see the bottle crashing. This is called crashing can experiment. The bottle will lose shape and you will see it being crushed. It's a clear show that there is atmospheric pressure. The can is closed. You cool it down rapidly by pouring cold water on it. It crashes instantly due to high atmospheric pressure from the surrounding. Take water. The force you place your glass upside down like this, inside you dip it water, then you will realize that the force caused by the atmospheric pressure acts on the surface of the card is greater than the weight of the water, and therefore water does not come out. There are several examples on that. So we were explaining on the crashing can experiment. Consider a tin container with some water in it. Sometimes a question is set, or now describe an experiment to show that there is existence of atmospheric pressure. So one of the experiments is crashing can experiment. Consider a tin container with some water in it. The container is heated for some time while open and closed after withdrawing heat. Cold water is then poured on it immediately. What is it? Like what we have said here. Hot water, then you close. It is observed that the container crashes inwards when the cold water is poured on it. This is because steam from boiling water drives out the air inside the container and a partial vacuum is created when the container is cooled. The higher atmospheric pressure from the outside crashes the container inwards. So at first, it has got this, the shape is not crushed before you cool it, because in that gap there is steam. So pressure from inside is equal to the pressure from outside, which is actually atmospheric pressure. But during cooling, the vapor condenses and therefore forms water. Where it has been occupying space, there is vacuum. And therefore, now the pressure inside is lower than the atmospheric pressure from outside. So the higher atmospheric pressure from the outside crushes the container inwards. Example, a sea diver is 18 meters below the surface of water. If the density of seawater is 1.03 and the gravitational field strength is 10 Newton per kilogram, determine the pressure on him and take the atmospheric pressure to be 103,000 Newton per square meter. So we can say the total pressure experienced by this person who is in the sea is due to the water above him. But there is also atmospheric pressure from the top. Like I can take a simulation here for that, for us to understand on what we are talking about. Taking on crashing can experiment. We can have a simulation to show us what is happening. Like here, we have on the surface here, we already have atmospheric pressure. You can decide to put atmospheric pressure off. On the surface, there is atmospheric pressure. So if you just put the atmosphere on, already the pressure gauge reads 101,312, implying there is already pressure here. And if this person was just deep inside here, if for example 3 meters below, let's see the pressure 3 meters below, this person will be experiencing 121 because of pressure due to the liquid above him, and on the surface here it's also acted upon by the atmospheric pressure. Let's do away with the atmospheric pressure and see whether it can be able to read the same answer here. Do it like that, you realize that pressure due to the liquid is only 20. If we put the atmosphere on, the pressure will be 121. So there is 100 that has come in due to the atmospheric pressure. So when we are deep in the sea or when we are swimming, there are two pressure acting on us. Pressure due to the liquid of the water in where we are swimming, plus the atmospheric pressure which is acting from the surface. You see, pressure due to the liquid itself is 20. Atmospheric pressure brings 100. So even if you bring this pressure gauge outside here, it already records 101. So implying atmospheric pressure is real, is working. So what were we saying? This person deep in the sea 18 meters is experiencing pressure due to the 18 meters of the water above him plus the atmospheric pressure. So you get the total pressure for this person is 18 times the density of the seawater times 10, then plus atmospheric pressure, and the answer will be 288,400. Like we have said in this simulation, like this person here is experiencing, if it was here, is experiencing 121, and 121, there is put atmosphere off, the pressure due to the liquid is 20. Put the atmosphere on, it is 121, implying the atmosphere is 101. Then you add the other one to make the total. That's what we are saying in our illustration here. So we move to measurement of pressure. How do you measure pressure? We use, that is measurement of atmospheric pressure. We use a U-tube manometer. U-tube manometer. It is used to measure gas pressure. It consists of a U-tube filled with suitable liquid to some level. Consider a U-tube manometer below, which one limb is connected to a gas supply. Look at this U-tube we are talking about. There is a liquid inside here. One of the limbs is connected to a gas. So what will the gas do? The gas will exert pressure on the liquid column around this region. and you see it going down. So chances are if it goes down, the other limb, the liquid will go up. Because this side is open, because it's open, what is acting on the surface of this water here is only atmospheric pressure, countering the pressure coming from here. So we can use this to measure pressure. How do we use it to measure pressure? You connect this to a gas, you want to know the gas pressure, and you already know the other side is only acting atmospheric pressure. Then you rate the gas in. You get to know up to what level does it push this liquid to. Then you draw a straight line. You draw a straight line. Then you say at this point here is point A, this point here is point B. So what do we have here? Pressure of the gas. What do we have here? At this point, point B, we have pressure of the gas, which has pushed this liquid upwards. But if you were also here as a deep sea diver, you will be experiencing pressure due to the liquid above you plus the atmospheric pressure. So what can we say? Pressure here is pressure for the gas. Pressure here is due to pressure due to the liquid column plus atmospheric pressure. So it becomes very easy. If you want to find the pressure of the gas, you say pressure of the gas at this point A is equal to pressure at B because they are at the same depth. Pressure at A equal to pressure at B. But what is pressure at A? Pressure of the gas. Pressure at B is pressure due to the liquid plus atmospheric pressure. So it will be height times density of the liquid times G, then plus atmospheric pressure. So the height is already here. So you find pressure due to the liquid column. Then plus the atmospheric pressure. So by that, because the atmospheric pressure is known, you only measure the height and the density of that liquid. When you do that, you sum, you get the pressure of the gas, where the density of the liquid is also known for that case. Let's look at an example. The height H of water manometer is, for example, 20. Let's say it is 20. And when used to measure this. So if it is 20 now, let's get the pressure of the gas. We say we draw a line here. Pressure here should equal to the pressure here. So we say determine the pressure due to the gas if atmospheric pressure is already 103,000. So we say pressure of the gas here is equal to pressure due to the liquid column plus atmospheric pressure. So we have got 0.2, that was the height, times 1,000 times 10 plus atmospheric pressure. So pressure of the gas is 105,000 Newton per square meter. So we have determined the pressure of this gas by getting the total pressure acting along this region, because pressure at the same level is equal according to Pascal's principle. So what will be the height if the liquid used is glycerin of density? Now the liquid has changed. The liquid is now glycerin. You only want to know what height that can this one be lifted. So we have already known the pressure of the gas. It is 105. So you only substitute in and substitute for density of this liquid, change it to kilogram per meter cube and multiply by 10, then plus atmospheric pressure. Substitute 105,000 equals to height we were determining times 1260 times 10, then plus 103,000 newtons. The other part is mathematical. You can just follow the workings until you end up finding what is the height. 0.16 meters. Correct? Then now we move to another example. The diagram below shows a mercury manometer. Some dry gas is present in the closed space. If the atmospheric pressure is 105 and the density of mercury is 13,600, determine the pressure of the gas. So that is the tube. Always said, take the lowest limb, the limb that has got the lowest level, draw a straight line to the other side. Then identify the two places. Say, for example, here X, say this side here, Y. Then you say pressure at X is equals to pressure at Y. So you can say this now. This tube here is open. So it tells you what is acting along this region is only atmospheric pressure. This side here is closed. So there is pressure due to the liquid column plus pressure of the trapped dry gas here. So you say pressure due to the liquid column plus pressure of the trapped gas should equal to the pressure at this region is only atmospheric pressure. Then you equate 0.25, 13,600 is the density of the liquid, then multiply by 10 plus pressure of the trapped gas equals to 105,000 Newton per square meter. Like what we had said, the pressure of this gas here. So you go with the substitution until you get pressure of the gas, which is 71,000 Newton per square meter. We are together at that level. Because you are given the atmospheric pressure as 105. So that's what we have replaced there. We want to move to mercury barometer. Mercury barometer. It is used to measure atmospheric pressure. It employs the fact that atmospheric pressure supports a column of a liquid in a tube. Just take an example here. We have an example for that. Yes, let's have an example. You have a liquid here. Just fill water, or okay, just fill mercury inside here. Then close the end. This is a tube. Then close the end. Then take the tube and invert it slowly. Invert it. Then you remove your hand and then make it stand upright. Correct? Make it stand upright. You see that? So you can see some liquid does not get out. It gets out up to some level, then it stops. So what is supporting here? You know, when already you have here, when you invert outside here, your thumb is closing the liquid not to come out. But the moment you invert inside here, you invert and you let your hand get out, there must be something replacing your finger. And that is actually, there is some kind of closing here. And that closing is simply because of atmospheric pressure working on the surface of this water, and therefore the water or the liquid or mercury here, the mercury is trying to look for a way out. So it closes here. As atmospheric pressure acts here, it closes here for the liquid not to come out. So this column supported here, if we measure this column supported here, then we can be able to get the atmospheric pressure of a place, because it is pressure due. If you are here, it is pressure due to the liquid column at this particular point. Yeah, so hope you have seen what to do. We invert. So we say construction of a mercury barometer. We have said the work is measuring atmospheric pressure. It is made by a thick wall glass tube, 1 meter long, like I've shown you, sealed at one end. The tube is then filled carefully with mercury to the top. Any bubbles in the tube are removed by closing the end and inverting the tube severally. The tube is then inverted in a dish filled with mercury. Mercury is preferred in the construction of a barometer to other liquids because it has got very high density, and that's what I've demonstrated here. Feel like that, that is the tube, close one end, then invert inside. By that, you would have made a barometer. So, that is how it looks. Here we have a vacuum. Some liquid will get out to a certain level, then what will remain here, we call it Torresian vacuum. You see, already when it is here, the liquid is complete. But the moment you invert, it's like some get out of this level. It tells you that this is the maximum level that can be supported. Past this level, it cannot be supported. So that is the pressure of that place. So what remains here, we call it, this gap here, we call it a Torresian vacuum. Torresian vacuum. So sometimes they draw a diagram in a question, then they ask you to label or mention the part here. What is the name? So how do we use this mercury barometer? We only measure the height. Just measure the height. Measure this height here. Then in that, after measuring the height of the column, that height is a measure of the atmospheric pressure. And we say pressure in liquid is given as height times density times pore of gas. So it's very simple. When somebody says that the pressure of a place is 76 centimeter mercury, that means the height supported by the pressure at that place is 76 centimeter. This height here is 76 centimeter. That is the height. So if you want to convert this pressure to pascals, it's very simple. You only multiply by the density of mercury, then multiply by 10. So it will be 0.76 times 13,600 times 10, you get 103,360 pascals or Newton per square meter. So you have sometimes seen pressure measured in millimeter mercury, like you get somebody saying 760 millimeter mercury. It tells you that the height supported is 760 millimeters. So to convert to pascals, just convert 760 to meters, multiply by the density of mercury, then by G. When they are giving it in terms of centimeter mercury or millimeter mercury, they must specify which liquid they are saying. So you will never see somebody saying that the pressure is 760 millimeter. No, it must be 760 millimeter mercury and all that, so that we can be able to know the density of the liquid we can multiply to obtain our atmospheric pressure of that place. So the atmospheric pressure at the sea level is called 1 atmosphere, or standard atmospheric pressure, which is 76 or 103,360. That is at sea level. Example, a student in a place where the mercury barometer reads 76 wanted to make an helical barometer of helical, which has a density of 800 kilogram per meter cube. What is the minimum length of the tube that this student would require? So you only need to find the atmospheric pressure of that place. So you say the pressure of that place, convert this one to pascals, then you say it's going to be 0.75 times 13,600, 10 times 10. You get the pressure. Then you say now, that pressure should equal if I was to use the density of mercury. So height of alcohol times density of alcohol times G. Because density of alcohol is given and G is given, you just substitute to get your H. And when you go like that, you get the maximum you require, or the minimum you require is 12.75 meters to support the same equivalence. A barometric height in a town is 70 centimeter mercury. Given that the standard atmospheric pressure is 76 mercury and the density of mercury is 13,600, determine the altitude of the town. The altitude, this question is very common. Determine the altitude of the town. So a place is 70. Then the standard one is 76. So that tells you there is reduction of reduction of, so from 76 to 70. So what do? Pressure difference. Pressure difference here is 6. The pressure difference here is 6. So is equal to at the sea level minus pressure at the town. So it is going to be 70 minus that. This is equal to the pressure due to the air above us. So it's going to be pressure difference. Then you convert it to pascals, which is actually 0.76 minus 0.70, 10 times 13,600 times 10 equals to pressure due to the air column above us, which is actually height of the air, height, that is in terms of altitude where we are, times density of air times G. And when you do like that, because the density of air is given as 1.25, you go a long way, then you end up with that you are at 652.8 meters. This is the altitude of that town. So I would request that you go again through this example for better understanding. The figure below shows a person sucking water using a straw. We have ever done this when we are drinking soda and water. You always ask for a straw. Explain how sucking is made. So what do you do to the straw? You only suck, my friend. You only suck air inside the straw. Then what happens is that the pressure inside the straw reduces the atmospheric pressure. Therefore, the pressure difference causes water to go into the straw and rise to the mouth. So it is the atmospheric pressure that pushes the liquid. What you only do is to draw air out. Testing of the vacuum in the barometer. Testing of the vacuum in the barometer. The vacuum is tested by tilting it, the tube. If the tube is fully filled, then the space in the vacuum, the tube is not fully filled, then the space is not a vacuum. So if you invert like this is faulty, this is not faulty, and this is the correct way. So you only test by tilting it. When you see there is a gap when you tilt, then know that there is air there, then it is faulty. So we want to move to some applications, and before we move to some applications, we need to understand on how to test the Theresian vacuum. So we move to siphoning. Siphon is used to transfer liquid from one container to another. The use of siphon to transfer liquid is due to the pressure difference called siphoning. So we will, in our next lesson, begin on the setup of siphoning as part of the application that applies atmospheric pressure.